Alrighty, gang, we're going to use the Gibbs Helmholtz equation to show that the freezing of water is spontaneous, so it occurs with no additional energy at negative 20 degrees Celsius and 1 bar. There's other ways to show that the process is spontaneous. I have other ways in the description below, but since it's asking to use the Gibbs Helmholtz equation, we'll do that. Now, what does it mean if it's spontaneous? Well, if the reaction's spontaneous, the change in Gibbs energy G is less than 0. This is true for a constant pressure and constant temperature process. And the Gibbs Helmholtz equation in all its glory is right here. This is in its integrated form. You can check out the other forms that I have in the description below as well. And it's important to pause for a minute to talk about what this actually represents. This is not an initial temperature, and this is not a final temperature. This is the change in Gibbs energy at T1. So if you were to freeze water at some temperature, say some T1 temperature, there'll be an associated change in Gibbs energy. And then if you freeze the water at a different temperature, say you freeze it at another temperature, there'll be a different delta G at that other temperature. So we're comparing the delta G's of the process at two different temperatures. Okay, we're not changing the temperature. Now, the change in enthalpy doesn't change because we're assuming it's constant, and at small temperature ranges we can. And that's what it means. Okay, so we're going to add a little bit of notation specific to the question. This is the change for the process of freezing, and this is under standard state, so this means it's a constant pressure of 1 bar, and it's pure water. And then I just transposed this term to the other side right here. So what we want to solve for is delta G, right? This delta G, and we're going to solve for delta G at T2. So T2 is negative 20 degrees Celsius. So what we need is to know a delta G at a different temperature. We have the delta H, that's given to us right here. So we need another temperature, and often we use the equilibrium temperature at 0 degrees Celsius. The equilibrium temperature is when both the solid and liquid phases are in equilibrium, and if they're in equilibrium, that the change in Gibbs energy at that temperature is 0. So that's cool. And then also this delta H, it's important to mention freezing is the opposite of melting. So notice this value is positive. That means energy is going into the system. So if water is gaining energy, if it's ice, if it's gaining energy, it's going to melt. So this is for melting. If we want it for freezing, we need energy to be released. So that of melting is equal and opposite to that of freezing. Okay, hope that helps. At this point, we can literally plug everything in. Notice this term is gone because this is 0 right here. And if we do that, solve for the change in Gibbs energy, we get negative 0.440 kilojoules per mole. It's negative, which means that the process is spontaneous. And if it's spontaneous, then the change in entropy of the universe is greater than 0 due to the second law, and life is good. All right, y'all, hang in there. The more problems you do, the better you'll get. I know when I took thermodynamics the second time, it was not easy. The more problems you do, the better you'll get. And I'll see you at the next video. And I'll see you in the next video.